In mathematics, particularly in dynamical systems theory, an Arnold tongue of a finite-parameter family of circle maps, named after Vladimir Arnold, is a region in the space of parameters where the map has locally constant rational rotation number. In other words, it is a level set of a rotation number with non-empty interior. Standard circle map. Arnold tongues were first investigated for a family of dynamical systems on the circle first defined by Andrei Kolmogorov. Kolmogorov proposed this family as a simplified model for driven mechanical rotors. These circle map equations also describe a simplified model of the phase-locked loop in electronics. The map exhibits certain regions of its parameters where it is locked to the driving frequency. Among other applications, the circle map has been used to study the dynamical behavior of a beating heart. The circle map is given by iterating the map where is to be interpreted as polar angles such that its value lies between 0 and 1. It has two parameters, the coupling strength K and the driving phase omega. As a model for phase-locked loops, omega may be interpreted as a driving frequency. For k equals 0 and omega irrational, the map reduces to an irrational rotation. Mode locking. For small to intermediate values of k, and certain values of omega, the map exhibits a phenomenon called mode locking or phase locking. In a phase-locked region, the values advance essentially as a rational multiple of n, although they may do so chaotically on the small scale. The limiting behavior in the mode-locked regions is given by the rotation number, which is also sometimes referred to as the map winding number. The phase-locked regions, or Arnold tongues, are illustrated in yellow in the figure above. Each such V-shaped region touches down to a rational value in the limitive. The values of in one of these regions will all result in a motion such that the rotation number, for example, all values of in the large V-shaped region in the bottom center of the figure correspond to a rotation number of. One reason the term locking is used is that the individual values can be perturbed by rather large random disturbances, without disturbing the limiting rotation number. That is, the sequence stays locked on to the signal, despite the addition of significant noise to the series. This ability to lock on in the presence of noise is central to the utility of the phase-locked loop electronic circuit. There is a mode-locked region for every rational number. It is sometimes said that the circle map maps the rationals, a set of measure 0 at k equals 0, to a set of non-zero measure 4. The largest tongues, ordered by size, occur at the Feri fractions. Fixing k and taking a cross-section through this image, so that omega is plotted as a function of omega, gives the Devil's Staircase, a shape that is generically similar to the Cantor function. The circle map also exhibits subharmonic roots to chaos, that is, period doubling of the form 3, 6, 12, 24. Chirikov standard map. The Chirikov standard map is related to the circle map, having similar recurrence relations, which may be written as with both iterates taken modulo 1. In essence, the standard map introduces a momentum which is allowed to dynamically vary, rather than being forced fixed, as it is in the circle map. The standard map is studied in physics by means of the kicked rotor Hamiltonian.